So we're talking about section 2.4 in your book, which says using derivative, and here's a new term, antiderivative formulas. Okay? So that's section 2.4. So we did that quiz last week. Your grades have been in Infinite Campus for a while now. Once we get everybody taking that, we'll got a couple people in the other class have to make that up, and so we'll get to take a look at those at some point. Right now, the plan is for a quiz next Monday. That's the plan. I'd like to do them on Monday, but that's pretty much when it'll have to be. We would probably be pushing it a little bit to be ready for Friday. And it's not going to be on Tuesday for sure. So it's either going to be Friday or Monday. It's either going to be this Friday or Monday. Okay. So anyway. So we've learned this power rule. So in chapter 2, think about what we did. We did the long way of doing the derivative, right, to find the rule. So we've come up with, kind of our old notation, our original notation. If f of x is x cubed, then what's f prime? 3x squared. Now the formula, what we're going to use a lot here is we're going to use this notation a lot. Right? The derivative of x cubed is 3x squared, right? So we learned that power rule. We also know that e to the x is its own derivative. We know that the derivative of sine is cosine, right? And so we learned that in section 1 and in section 2. We talked about those things. Of course, section 3 was kind of a side trip where we went into limits and talked about limits and all that because the definition of the derivative was about limits. So now what we're going to do here in sections 4, the book kind of skips around, but in sections 4, 6, and 7, which is kind of the order we're going to go right now over the next 2 days, then we're going to be learning more. We're going to really investigate more of these derivative formulas. We're going to start coming up with a list of rules for these derivative formulas. Now let's just talk about antiderivative here just a minute. So what in the world does antiderivative mean? If f prime is the derivative of f, no, that's the second derivative, right? The second derivative would be that, right? And then the third derivative and the fourth derivative. In other words, we could just keep going in that direction, doing the derivative right over and over and over and over again. What do you suppose the antiderivative would be? What do you mean? Use it in a sentence. Then it makes sense that the antiderivative would be going the other way, right? So if you use it in a sentence, the derivative of f is f prime. Now use antiderivative in a sentence. The antiderivative of f prime is f. That's right. And the antiderivative of f double prime is f prime, right? The antiderivative of f prime is f. It's just going the other direction. It's just going the other direction. Now, we are going to have to introduce some. Now, so let's talk about this. Could we do that? So let's pretend that we were given f double prime is 6x. And we had to figure out, well, what must f prime have been? It's not like we're going to have a whole new rule necessarily. It's just really going to be thinking backwards, right? Because we know by the power rule, if the second derivative was x to the first, what had to have been the derivative right before it? It had to be x to the second, right? And of course, we know the rule is when you bring the 2 down in front, right, you're going to multiply by whatever's there and end up with a 6. So there must have been what there? There must have been a 3 there, right? There must have been a 3 there. And then you say, well, what would have been the antiderivative of that, right? Well, it must have been an x
cubed. And when you bring that 3 down in front, it's got to give you this. Well, there must have been, just a 1 there, right? Does that make sense? Now, here's where it gets interesting. So derivative, we get that. So if I ask you for the derivative of f prime, derivative of f prime, f double prime, derivative of f double prime, f triple prime, and whatever, we keep going over wherever we do. We go the other way. Antiderivative of f double prime is f prime, antiderivative of f prime is f, but what if I said to you, what's the antiderivative of f? But does it make sense that there is an antiderivative of this? Isn't there some function that when you do its derivative would give you x cubed, right? So here's the notation we're going to use. Big F. Big F. Now, that leads, of course, and we'll find it here in a second, but that leads to the obvious question, what's the antiderivative of big F? Bigger? No, it couldn't be big F prime, that'd be the derivative of big F. I'm saying the antiderivative of big F. We want to go up. Keep going up. What's the antiderivative of big F? Great big F? Really, really big F? No, we can't. We never do that. We never go another antiderivative, right? I mean, so now it's going to be really important when we say F in here, and I haven't noticed it with any of you guys. Sometimes I get people when they do their f of x, they always make it capital F, and it never mattered until now. Now it matters. So when I talk about F, I mean little f. I don't want to have to say little f all the time. Now I will. You'll hear me say little f, right? But when I say F, I mean little f. So if we mean big F, we better say big F or capital F or uppercase F. I usually say big F. Okay, it matters. Now, what would it be? Well, it'd have to be x to the 4th. Now, what number would have to be here so when you bring the 4 down? There'd have to be a 1/4 then, right? Now, we can actually write that as a rule. The antiderivative of the power rule, normally, I'll be honest, we're not going to get in antiderivatives a whole lot until after Christmas. Antiderivatives will be a much bigger deal, but our next quiz will be a couple, just simple ones. Basically, the idea of an antiderivative is kind of guess and check. Derivatives, we're going to have rules. If you want to do the derivative, do this. Bring the power down in front. Multiply, you drop the power by 1, right? Antiderivatives are a little more of an art than a science. They're more like, okay, what must it have been so when I do the derivative, it gives me what I want, right? That kind of thing, like what we're doing right now. Now, with a power rule, we can do it. If you think about it, the derivative is what? You multiply, you bring the power down and multiply, and then drop the power by 1. So let's do that in reverse. So in reverse, it would be add 1 to the power, and then instead of multiply, it'd be divide by new power. If you think about it, that's the rule. Now, here's how we usually write it. X to the n plus 1 over n plus 1. That's how we usually write it. And if you think about that, that worked all the way up here, right? If we start down here, at the bottom and do that, this would work, right? So antiderivative, raise that up to a 2, and then divide by the new power. Divide by 2. What's 6 divided by 2? 3. Raise that up to a 3, and then divide by 3. The 3's cancel, right? Raise that up to a 4, and then divide by 4. Now, I don't like to write divide. As you guys have seen me this year, I'd rather multiply by a fraction because that's just going to be better for us. The divide you're going to see in the next week and a half or so especially. But so I would raise that up to a 4, divide by 4, I would just write it 1/4. Okay? Now, here's the other thing we have to understand. Here, the last thing I want to talk, well, I'll tell you what, this would be a great time to look at this picture. Okay, let's say that you don't need to write this down or anything, but let's just say that I told you that this right here was f prime. And I wanted you to draw an f graph. in blue. Okay? Well, what would be going on right here? No. Come on now, we did this back in chapter 1. This is going to be key for what we're doing today. The red is F prime. It'd be a local max or local min. Which one? Emily? F prime going from negative to positive mean F is going down to up. There's going to be a local min right there, right? What we care about down here, that this is negative. So what's my blue graph doing? My blue graph's got to be coming down, right? And it's got to be bottoming out like that, right? Then it's positive until here. So that means this graph is going up until right here. This is when I would have my inflection point. Now it's positive and getting less positive until we got a local max right there. This is going positive to negative right here, local max. Then it's going down until right there, inflection point, and then it's leveling, got a local min again, and then it's doing that. Wouldn't that be our F graph, something like that? Now, what did we say when you draw that blue graph? Where do you draw that blue graph? It can be shifted anywhere, right? All we knew is this graph was going down. We don't know exactly. That's where it could be shifted anywhere. Okay, now I want you to watch something here. What do you do when you take the derivative of, say, 6x plus 7? What's the derivative of that? Oh, wait. If you had 3x squared plus 7, what's the derivative of that? 6x plus 0. What's the derivative of 3x squared plus 12? What's 3x squared minus 8? What's the derivative? Okay, so when we're doing the antiderivative, so if we have 6x and we do the antiderivative, we raise it up to a 2, we divide by 2, that gives us 3x squared. How do we know whether there's a minus 8 there, or a plus 12, or a plus 7? We don't, right? Think about what we just said here. When we go and do an antiderivative, let's do this line right here. When we go from F prime to F, just like we did on that graph in chapter 1, when you have an F prime graph and you go to the F graph, do you know where it is this way? You don't know. There's a lot of different options. So when you go from an F prime equation to an F equation, do you know that that's the equation? Couldn't it have been that? Right? Couldn't it have been that? Right? Wouldn't all of those have this same derivative? Right? You see what I'm saying? Because what's a plus 3 do to that graph? Right? So here's what we're going to do when we do an antiderivative. We're going to tack on a plus c as a constant. There could have been some constant there that we just don't know about. Okay? And of course, if there is, then that's going to affect our antiderivative as we go up the chain, but we're not going to do a whole bunch of antiderivatives, so I don't want you to worry too much about it. But just understand this aspect of that antiderivative is just the idea of working backwards. Now, you might remember when we had our chart, and I left this blank over here, and I don't know if any of you were wondering if you thought I was just lazy or something, and why I didn't put F prime and F double prime in our chart like that, right? And we talked about how F prime and F double prime have the same relationship as F and F prime. Well, now, couldn't I have done this? Here's why I didn't do it. Because couldn't this line be F? Big F? Then what would this line be? Little f. And then this line would be little f prime. Now, isn't it also true that this line would be big F prime? Right? What's big F prime? That means the derivative of big F. Well, isn't that the same as little f? Those two are the same thing. Big, so that might be something to write down too. Big F prime is the same as little f. Big F prime is the same as little f, because that's what we defined it to be. We said big F was the antiderivative of f. That was going up, going that way, right? Antiderivative. So going down is derivative. So this would be big F double prime. Big F double prime would be the same as little f prime, right? But usually, I'll be honest, we don't use big F prime very often, right? We talk about the derivative of big F, we say, oh, that's little f. right? Derivative of big F is little f.
And then, of course, the derivative of little f is f prime and little f prime and so forth.
Okay, just some notation. It hasn't changed a thing. The chart is still the chart. The relationships are still the relationships. Okay, so back on this graph, okay, and let me pull up that, I've actually got the green is the F graph, okay, but couldn't I have called the red F? Oops. Couldn't I have called the red graph instead of F prime? Couldn't I call it F? Then what would my green graph have been? Big F, right? So I could have called, I called the red graph F prime earlier, and then we said the green was F, but it could have called the red little f, and then the green would have been big F, the antiderivative. Okay, so just some thoughts there on some notation. Okay, so now what we want to do is we want to actually use those. Okay, so it's a great example of what we just did there with the chart. If I've got F prime, we figured out that there were local max and mins. As a matter of fact, this point right here, this point right here, and this point right here are really important points on this. If we call this F prime, if we call this graph F prime, then where F prime is 0 are really important points for us, right? And not only that, but these were too. These were inflection points on F, weren't they? Okay, one of the things that we're going to be doing, working out today, is if I give you an equation for F, I want you to be able to find its local max, its local min, flat spots, where's it increasing, where's it decreasing, all that chart stuff that we did back in chapter 1 when we had graphs, we're now going to do those with equations, with the formulas. Okay, so we got to talk about how they make. Now it's really easy to see where this graph is 0, right? The first thing you guys looked at is when I said, where is F prime 0? You just looked at it, boom, 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 there it is. Well, when you have an equation, that's not as easy. What are you going to have to do to find where an equation is 0? You're going to have to solve it, right? You're going to have to solve the equation. Remember those worksheets we've been working on with solving equations? That's where this is going to come in, and that's why we're doing it. And to be honest, you're going to do a lot more of that as we go through the year than you are going to do the graphs. We started, though, with the graphs so you guys would get a sense of the chart relationships, how that works. But now we're going to focus on these chart relationships and stuff when we use equations, okay? And you're going to go back and wish we were using graphs again. You know, because the graphs are nice. I mean, you think about it. Think about how nice it is. If you know that this is F prime, you just got to go negative, positive, positive, negative, negative, positive, right? So you know, okay, we got a local min, we got a local max, right? We got that. So what we're going to try to do is we're going to try to use that to our advantage. We're going to take the way we work with graphs, and we're going to do that with equations and try to make it as similar to that as we can. Okay, so open your books to page 112. Open your books to page 112. Okay, we're going to talk a lot about extrema today. And matter of fact, on my goal thing over here, you know, it says, what are we doing? We're finding extrema of functions. Extrema is just a fancy word for max and min. Okay, fancy word for max and min. Now we got two types of max and mins. Okay, so we've got local extrema, okay, which would be like this or this. Now we also could include where the derivative is undefined, but we're gonna probably stick with pretty nice functions for right now. Remember we said differentiable means where the derivative exists. Differentiable means where the derivative exists, so that would rule out those sharp points. So mostly we're going to think about stationary points here. We're going to talk about where the derivative is 0. Okay? I'm going to just say right now, no endpoints. When we do a local max or min, we want to be able to see on both sides of it. Okay? So we're not going to talk about endpoints being a local max or min. Okay? So we're talking about peaks and valleys. And then the other type is global. Oh, another word, let me put that in blue, that's sometimes used is relative. In the older books, they used to talk about relative max and relative min instead of local. Okay? Now the one we haven't talked much about is global extreme. And the other term that is sometimes used is absolute max and min. But more and more now the books talk about global max and min. Global extrema is the highest and or lowest outputs or Y values, right? It's the absolute highest point on the graph and the absolute lowest point on the graph. Okay, now that could be here, that could be here, but it also could be at an endpoint. It could be like that, right? The highest point could be at an edge. Now, it also could be at a sharp point, but if we eliminate for right now, let's just say we're going to work with nice smooth functions. We may run into some here in the early going, but I don't think very often we're going to. So if we assume we have nice smooth functions, a derivative exists everywhere, no sharp points, okay? But it's the highest and the lowest output. So, on page 112, at the bottom of the page, it says, let f be differentiable on an interval I. Okay? So that means we have like a closed, like endpoints. Okay? The max and min values. Now notice it didn't use the word global or local, but just reading that sentence, which one are they talking about? The max and min values of f. They're talking about global. Right? If the word local or global isn't in there, they'd probably talk about global. Now, here's another key thing. Let me put this in here. Global extrema, we usually want outputs. Okay? They'll usually say, what are the max min values? They'll use the word what. What are the max min values? And so they're wanting the outputs. What is the highest point? Okay? Up here for local, we usually say where are the local extrema. Usually want inputs or x values. There's a local max at x equals 2. There's a local min at x equals 4. We want to know where they are, not what they are. Think of the sine graph. What is the max value of sine? 1. What is the min value of sine? -1. We don't care. It happens in a whole bunch of different places, right? So we don't care where it happens. We just want to know what is the max value. But if I say where are the local maxes on sine, then I'm talking about all those x values. Okay, very important that we answer that question that way, that we don't give information they're not asking for. If you go back to this graph, like when I put those points there, if I asked for the stationary points, I would never want you to give it as an ordered pair like that, right? We would say the stationary points are at x equals -3, x equals 1, x equals 5. That's what we care about, right? We don't want that. As a matter of fact, those aren't even on f. If I say, what are the stationary points of f, you can't give the point 1, 0 because that's not a point on f. 1, 0 is a point on f prime. Okay? So it'd be wrong to answer the question that way. All right, now, the fact that they state there, max and min values can only occur where f prime equals 0 or at endpoints. Now remember, this is called a stationary point right here, where f prime is 0. So that tells us those are the only places we have to look. If we want to know the highest and lowest point on a function, now it's got to be differentiable, so it can't have any sharp points, no breaks, none of that stuff that we talked about last week with discontinuity. We can't have any of those kind of weird piecewise kind of things going on. If we have a nice, smooth, differentiable function, then boom, we know we've got, and there's a closed interval. I mean, if you just look at the x cubed graph and don't, and talk about all reals, if you don't have a closed interval, there is no highest point, right? There is no global max. There is no global min. It just goes forever. Or you take a parabola, a normal parabola would have a global minimum, a low point, but it wouldn't have a high point, right? But if you lock it in between some endpoints, there's got to be a highest point, and there's got to be a lowest point. But it could be one of each. Like, for example, you could have this, right? The max is at the right edge, but the min is at a local min. You see what I'm saying? But it's got to be at one of these places, right? I mean, you think of a nice smooth curve, you can't think of any other alternative. The highest and lowest point either has to be where the derivative is 0, or it has to be at an endpoint. So that's great, because that gives you places to check. Okay, if we're looking for local extrema, then all we're looking for there is where f prime is 0. Because we just said no endpoints. Right? So we're just looking for the stationary points. So local max and min, we just look where f prime is 0. Global max and min, we look where the f prime is 0, and we look at the endpoints. Okay? Now, again, a couple other things. Here, how do we tell then what's the global max and min? Well, it's whatever has the highest y value. So we're going to take our stationary points and our endpoints, and we're going to plug those back into the original function. We got to see the y values to know if it's a high point or a low point. How do we tell if something's a global or a local maximum? How do we tell if this is a local max or min? If it changes from negative to positive, if the f prime changes from negative to positive, right? So that hasn't changed. So the way you tell if something's a local max or min is we don't care about its y value. That's not going to tell us anything. What we care about to be a local max or min is, does f prime change from positive to negative? That's how we tell if we have a local max min. Okay? But to tell if we have a global max min, we have to take our places where the derivative is 0 and our endpoints, and we have to plug those back into the original function, see what their y values are. The biggest one is our max, and the littlest one's our min. Does that make sense? So there are two different things we're doing. Now, they're going to start the same. In both situations, we want to do the derivative and see where it's 0. Okay? But we're asking for two different pieces of information. So this one, we got to see if it changes to make it a local max or min. This one, we got to plug it back into the original. Okay, so we got a couple different things going on there. All right. So let's do some examples. So if you turn in your book to page 121, this is number 24, and this is very much like a homework problem you have. You're going to do number 23, and you're going to do number 25. So this is going to be, more than nice of me to give you the odd ones, right? But then again, you're going to need a lot more work than just that. There's going to be a calculator part to this and a no calculator part to this. These problems we're about to do right here are really kind of critical kinds of problems. We'll do a lot of problems this year that are helpful in understanding our concepts, and they're good problems, and they make us think and whatever. But then there are also problems we're going to do this year that are just foundational, fundamental. Every calc class has them. They're going to be on the AP test. They're going to be on our midterm. They're going to be on the final. They're just very fundamental types of problems. Well, this is one of them, right? Okay, problems like the ones we're doing today are one of them. There's 6 free response questions on the AP test. Those 6 questions typically are over kind of the big ideas, the very fundamental type problems you have to do. There's always one similar to the type we're doing today is usually one of those 6. Okay? All right. 24 says, find the max and min value of the function over the given interval. So which one of our max types are we finding? This is a global max problem. Global max min. Notice they give us an interval here. Oops. Now, let's assume for now, for today's homework, it's all no calculator. No calculator. Now, I'll talk as we go along what a calculator problem would look like. Now, you might say, oh, if I had my calculator, I just graph it. I would trace to the highest point, trace to the lowest point. That's not good, right? On a calculator problem, I'll show you how you would get points on this problem, okay? All right, so back to this page. It's a global max problem. What do we need to look for? We need to see where the derivative is 0, and we need to check the endpoints, which of course they just gave to us, right? So we need to do the derivative. Now remember earlier this year I said, when you don't know what to do in a problem, do the derivative, set it equal to 0. This is the kind of problem I'm talking about, right? So we're going to do the derivative, which of course we've learned our rules. This is, of course, remember the title of this section is using our derivative formulas. Using our derivative formulas. All right, so what's a derivative of 1? 0. Derivative of 2x cubed? 6x squared minus 4x cubed, and then put equals 0. If you don't put equals 0, you might lose a point. Put equals 0. We want to see where the derivative equals 0. Now, here's where you could use your calculator. Now, if you can't do those two derivatives right there, then you've got bigger problems in being able to do the next one, right? That shouldn't be an issue. But if, let's say it was a little tougher kind of function, and you weren't sure on the derivative rules because we're just starting them, you could, on your calculator, have it do the derivative for you, okay? And we'll talk about that later. Because I wouldn't know. How do I know if you did that in your head or did it in your calculator? I have no idea, right? Now, obviously, if it's no calculator problem, I would know. You're not using your calculator. All right. So it is okay to let the calculator do the derivative for you if it was a calculator problem. Now we've got to solve that, right? If it's a calculator problem, you could do solve on your calculator right? Whatever work you do here is up to you, whatever you need to show. I'm not going to give you algebra points here, okay? But, so you're going to get a point probably for doing that. Now, what would we do to solve this? Factor out an x squared. You could take out a 2. It's not really necessary, but you could. But you want to take out an x squared. So that'd be 3 minus 2x equals 0, right? So then 2x squared equals 0, or 3 minus 2x equals 0. So here you divide by 2 is 0, you square root, it's still 0, right? And then here you would add 2x over there. How much of this you show is totally up to you. And then what would that be, 3 halves? 3 halves. Now, the other thing you should check is, are those in your interval? Are those between -1 and 2? And they are. If you get one of these that's not inside your interval, you just throw it out, right? You just throw it out. Okay, so if this was a calculator problem, you wouldn't have these lines on your paper, right? If this was a calculator problem, let me do in red what you would have if it's a calculator problem. If it's a calculator problem, you would have this on your paper, and you would have this on your paper, right? You would have both, but you'd have to have those things. You couldn't just graph the F-graph, trace to its high point, trace to its low point. You can't do it. Now, could you do that to just check to see, if you're getting the right answer? Sure. All right, so the black would be if this is a no calculator problem, which we're going to assume on our homework, let's assume they're all no calculator, okay, because that's the kind we want to practice the most, okay? All right, so now, what do we do now? We want to see, so we got our endpoints. We know where f prime is 0. That's the only place the high and low points can be. How can we tell if they're a high or low point? How can we tell which one of these x values has the highest y value or the littlest y value? Put them back into the original function, the one we're trying to find the max and min of. I call this a list of candidates. A list of candidates. The problem will always say, well, it may not always say, you are always required to justify why you have your answer as the global max or min. The list of candidates, and this works on the AP test, is a fine justification. This shows that you're checking all the possibilities of where they could be. Now, here's how I want you to write that. So we're going to plug them back into the original. So that means we need to know f of -1. We need to know f of 2. What order you put these in doesn't matter. We need to know f of 0. And we need to know f of 3/2 or 1.5. Now remember, this is no calculator, right? But even if this was calculated, we would have you would have the red, and you would have this, right? So even if this was calculator, okay, so red is if it's a calculator problem. Right? And the black is if it's no calculator. So it's pretty much the same. You pretty much have to have the same stuff there. Okay? Now, the only thing that would make me a little leery about this one being a no calculator one is now you've got to take 3/2, you got to do it to the 4th power. Right? It's going to get a little ugly there. Right? We're going to go ahead and do it, but probably not going to make you do a whole bunch of that. So you don't have to worry too much. Let's put a -1 in there. So -1 cubed is -1 times 2 is -2. -2 plus 1 is -1. -1 to the 4th is 1. So -1 minus 1, that's going to be -2. Put a 2 in there. 2 cubed is 8 times 2 is 16 plus 1 is 17. 2 to the 4th is 16. 17 minus 16 is 1. Put a 0 into there. That's easy. That's 1. And then 3/2. Okay, so 3/2. So 3 cubed is 27. And 2 cubed is 8. And then times 2, that'd be 54 over 8. What's that? Almost 7? 7 plus 1 is almost 8. Usually you can get in the ballpark, right? If this was a test, I would be trying to get that a little more accurate. So I would be going, well, let's just do that. So if that's 54 over 8, 1 would be 8 over 8, right? 8 over 8, so 8 plus 54, it's at 62 over 8. And then what's 3/2? So 3 to the 4th is 81, and 2 to the 4th is 16. So it'd be 62/8 minus 81 over 16. You are advanced placement students. We should be able to do 8th grade fractions, right? Okay. But we're not going to love doing them, and we're not going to have to do them a lot, but we should be able to do them. If I want to get a common denominator here, this would be 124 over 16. 124 minus 81 is 43. So 43/16. Right? And what is 43/16? That's about 2 and 11/16. Would that be right? 16 times 2 is 32, with 11 left over. Okay, so then I would write max by this one, and I would write min by this one.
Does it matter if you write it as a base number?
Nope. 43/16 is fine. 2 and 11/16 is good. And if you want to do some long division and divide it out, you better be right to 3 decimal places. So I would never do that. Right? Why do that? Leave it as a fraction. Matter of fact, it doesn't even have to be a reduced fraction. I don't even care about that. It has to be a correct. Either way, 43/16, 2 and 11/16, either one. But I just did that so I could tell if it was bigger. Right? I just wanted to know where it was in the max min thing. So look what you got. You got a max that was at this stationary point, and you got a min that was back at the left end point. So what we must have had was an F graph that was down here, came up at 0, and then at 2, and then it must have come back down, and then came back, and then where was the max? Oh, wait. So this is a 4th degree, so it probably, I think we had a flat spot here at 0 probably. So I think it flattened, then went here, and then came back down, and then it was, the min was here, the max was here, and then back at 0 it came back to about here. I think it was something like this. Okay? So I think what happened was we had a minimum back here at -1, then at 0 we had a flat spot, then it kept going up, and we had a max here at 1.5, and then it went back down, and it was at the same Y value. These two have the same Y value, so they had the same Y value there. So I think we had that kind of situation. Doesn't matter that you draw it, but we had a min at an endpoint, and we had a max. Okay, that is a classic global max-min problem. Guaranteed you will have one of those will be worth 5 or 6 points on the next quiz, right? Get a point for doing the derivative, setting it equal to 0. Get a point for solving it correctly. Get a point for your list of candidates. Get a point each for the right and wrong there. That's probably 5 points right there. Okay? If it was a calculator problem, you would have all of this except for really maybe this work I did right here, right? And I wouldn't have had to do all this, this messing around here, right? I'd been able to just type into my calculator and get those values easily, right? If it was a calculator problem. So that is a global max-min problem. Put that great big on your paper, global max-min problem. On our website, if you remember, I had some videos down here where it says max-min inflection point review videos. Here's a global max-min example that I worked out a few years back. Matter of fact, it might be this exact problem. Now that I look at it, here's f prime. I think it says 6x squared minus 4x cubed. Isn't that what we just did? I think it's that exact problem. It's my example, okay, that I did. So there it is worked out. So if you want to see that, of course, we got here. And I also have a local max-min. I got a local max-min with a no calculator. I got an inflection point, and then this is another thing. So these are some old ones that I did that are certainly here for you too. So you can see it's a pretty important concept, right? I made some separate videos for those. I even had strange people on the internet look at those and comment in the video, hey, thanks. I think if we go to, I don't remember which one, hey, thanks, it's a great video. It really helped me. Thanks. You're welcome. So I must have done some search for Max or something on YouTube. I don't know. So I'm sure it's a real popular one. Probably has all 7 hits or whatever. But anyway, all right. There's a classic problem. I don't want to spend a lot of time doing it because we're not going to get big into story problems right now. But there's the classic calculus problem. We'll do this later. It's called the box problem. If I don't even write this down. If I was going to take a piece of paper, this is going to be a chapter 4 thing, and of course the hard part of this will be getting it set up. But if I was going to take a piece of paper, cut out the corners, cut a square out of each corner, right, like this. And then fold it up to make a box, right? Everybody picture what I'm talking about there, right? So I'm going to cut these corners out. I'm going to fold this up, fold this up, fold this up, fold that up, right? Make a little box. What size corners should I cut out so that the box would have the maximum volume? Okay? It's just a classic example of where you might want to find a maximum. Because if I cut out too big of pieces, I won't have a max. If I cut out too little, then it won't be very tall, right? If I cut out little tiny ones, it won't be very tall at all, and it won't have very much volume. So what size square should I cut out? Well, it would look something like this. Let's make nice numbers here. So let's say this was 8 inches on the side, 12 inches on this side. Let's let x be the size of the square that I cut out. I want them all to be the same. So what should I cut out? Well, what I need is the volume of a box. Well, the volume of a box is length times width times height, right? Well, if I cut this out, now my box would look like, if I want to draw my box here, okay? right? I'd have something, that's not very good, but whatever, I'd have something that looks like this. Now, how tall would this box be? If you fold up these edges, it'd be X right there, right? What would this side, let me do it in blue, what would this side right here be, which would be this side? 12 minus 2x. And then what would the red side be right here, which would be this length right here? This would be 8 minus 2x. You with me? Okay? So, my volume would be x times 8 minus 2x times 12 minus 2x. Would you agree? That would be the volume of that box. Okay? Now, I could go ahead and I could FOIL that out, right? I would get da-da-da-da-da-da-da. And now that would be exactly the same as this problem right here. And then I would have some endpoints too. What's the littlest that x could be? 0. Then you wouldn't have anything cut out. You'd have no volume. That's easy. 0, you'd have 0 volume. So that's clearly not a max. What's the biggest x could be? No. Littler than that. 4, right? Because if x is 4, right? If x is 4, and then when you cut that side, you cut out that whole side, right? You'd have nothing to fold up. So the littlest x could be would be 0. The biggest. Now this is a chapter 4 thing. You're not going to have to do these story problems in chapter 2. Chapter 4, we're going to have this, right? I'll say, hey, you have an 8 by 12 inch piece of paper. You're going to cut squares out of all 4 corners. What size square should you cut out to get the max volume? This is how you go about it. You say, oh, I need an equation for the volume. You draw yourself a picture, blah, blah, blah. And we'll practice a lot of different scenarios, right? But it's always tricky because you got to get the right equation set up. But now we're ready to do what we did here, right? We now have our endpoints. We have the thing we're trying to find the maximum of. And so now what do? We do the derivative, right? So we would do the derivative. We would set it equal to 0. We would find what those x values are, however many there were. We would take those x values and those x values, we plug them back in and see which one gives us the most volume. Which one gives us the most volume. And then that's the size of the square we should cut out, because that's what x is. Okay? So that's a classic example of why we might want to do a max min. Okay? A business might find a profit equation for so many units. How many units should they sell to get a maximum profit? You might have a snowmobiler stranded in the snow, and he wants to know the minimum time. Right? I know they're kind of silly. Matter of fact, your book even talks about that on page 114. They talk about real world, and they're not all that realistic, but the basic principles are important. So that's why we do it. All right. So moving on. Let's take a look at number 20 on page 121. And that, I think, might be the other one I have the video of. I don't know why I'm doing this again. I should just make you get your Chromebooks out and watch the video, and I can put my feet up over the chair. Oh, well, I might as well get paid here. Make it. I guess I'm getting paid no matter what, but make it worth taxpayers' money. All right, so number 20, we got this. This. Okay, now this problem, and guess what? You're going to do number 19 on this one. That might be the only one of these you're going to do for tomorrow, so you're going to do one very similar to this, okay? Yeah, the assignment, I know you're looking on the assignment sheet, and I'm going way off the assignment sheet right now, yeah, because we redid things because of Thanksgiving falling weird and so forth. So it's going to be a weird assignment, not on the assignment sheet. Matter of fact, the rest of the chapter will pretty much go away from the assignment sheet. All right, anyway, so here's a function, but now the question is different. Now the question is going back to this kind of question, what I call chart stuff. Chart stuff. Okay? So now look at the question. It says, answer each of these about the given function. Express your answers exactly. For example, square root of 3 rather than decimal. Well, what are they telling you there? What do they tell you? They're telling you no calculator. That's what they're telling you. Because our calculators will leave it right on 4, right? They're telling you no calculator, right? Now, I already told you that. Assume these problems are all no calculator, okay? You've got to practice them that way. All right, so the question, A, where's the function increasing? B, where's it decreasing? C, where's it have a local max? D, where's it have a local min? So, you look at those questions, and you are probably saying to yourself, man, if I had a graph of f prime, this would be so easy, right? Where is the function increasing? When f prime is positive, right? When f prime is positive, the f function here would be increasing. Where's f decreasing? When f prime is negative. Where is their local max? When f prime changes from positive to negative, right? If I only could have the graph of f prime, this would be so easy. But it's no calculator, and all I have is an equation, right? So we're going to try to mimic that. But if we had an f prime, and we had this information on it, if we had that information about f prime, wouldn't this be a really easy question? Right? If we had the minus plus information about f prime, this would be a really easy question. So here's how we're going to do it. Here's how we're going to do it. So the key to the plus minus is these 3 points, right? The key to the plus minus thing is where is f prime 0, right? When you do a chart, the first place you look is where is f prime 0, right? So we need that. So that's what we're going to do. And we talked about it back here. We want to see where f prime is 0. Any of the chart questions start there. So now this happens to be s prime, but that's fine. Same thing. Okay, so this would be negative 72 t to the 8th plus 72 t to the 7th, and the 7 goes away, and then we write equals 0. Same thing we started the other question. They start out looking the same. Because they both want, a big part of the problem is where is the derivative equal 0. So we got to start them there. All right, what do we do to solve that then? Okay. A lot of times people take out a negative whenever the leading one is that. T to the 7th. And that would leave you with t minus 1. Would that be right? So when you solve that, either t equals 0 or t equals positive. Positive. Now I usually label those. I didn't, I don't think, on this other screen. I usually label those as my stationary points. I like to label those. Okay, those are my stationary points. Well, guess what we just found? We just found where f prime crosses the x-axis, right? So you think about the chart. What would really, don't write this down, but what would really be nice to know is now what's it do? Does it come down and do that? Because that would tell us positive, negative, positive, right? Or does it come up and do that? Right? It can't cross anywhere else. So we know it doesn't go up, come down, come up. We know that because it only crosses at these 2 points. We know that. So it's got to go up and then do that. Now I suppose it could come up, just touch, come down, and then go back like that. Right? Couldn't it do that? It could just, we don't know, right? We don't know which one of those it does. Is it negative, negative, positive? Is it positive, negative, positive? Is it negative, positive, negative? That's what we want to know, right? Well, here's how we're going to do it. We're going to do what we're going to call an f prime number line. You're going to do a ton of these this year. We're going to do what's called an f prime number line. And we're going to label it, and we're going to go like this, and we're going to put a 0, and we're going to put a 1 there. Whenever you're doing chart stuff, this is what you're going to do. Okay? We're trying to mimic the information we had when we had f prime graphs. right? Because if we had an F prime graph, man, we had it down. We had all that information about F. We had all the chart stuff was all there for us. Okay? All right, so we're going to mimic that. Well, what do we want to know? We want to know if it's going plus, minus, plus, or minus, minus, plus, or what's it doing? That's what we want to know. Okay, well, how do we tell? How do we tell if F prime is positive, between 0 and 1? We don't have a graph, but we do have an equation, right? We got an equation for S prime right here. Put in numbers. Let's put in 0.5. What can we put to check over here? Well, this is no calculator. So do we really want to put in 1.5? Wouldn't 2 be a lot better? Wouldn't -1 be a lot better here? Do you notice they didn't give you any endpoints here? We don't care about endpoints, right? Local max and mins do not happen at endpoints, right? We're not going to even care about endpoints for local max min, okay? So here I got no choice. I got a 0 and 1, I got to put in, Now I probably won't put in 0.5, I'll probably put in a fraction. That'll be easier than the decimal, okay? And so yes, I'm going to put those, now notice how I did my number line, because this drives me crazy when people do this. Notice how I only put tick marks on the 0 and the 1. You don't want to come in here now and put tick marks on these numbers. That's not what we want. We want to know what's in between the tick marks, right? So I take my stationary points where the derivative is 0. That's like these dots right here. I want to label those. So I put tick marks there, okay, for my stationary points. And then I write numbers in between. Now, I did them in blue. If you just want to make them real little, for some reason, this really confuses people when they put their numbers on here. And they put, it just gets so confusing. So a lot of times what I'll do is I'll write them really small. I don't know, something, anything to help. I just want you to know that these numbers are a lot different than these numbers. These numbers are important. They're in my answer. They're where my local max and mins are going to be. These are just numbers I'm sticking in there to see if I've got positive, negative, positive, see what's going on. All right, so let's put a -1 into here. Now, I could also put it into here. What do you suppose would be easier to plug into? Remember, all I need to do is see what F prime is. Now, remember, on this problem, we were plugging back into the original, right? Now, people are going to get confused. I don't remember what to plug into. Think about what you're trying to figure out. Here, we're trying to figure out where F has its highest and lowest Y value. So you've got to plug into F to be able to see what the Y values are. Here, we're trying to see if F prime is positive or negative for the chart. So we've got to plug into F prime, right? That makes sense? So if you know what it is you're trying to figure out, you shouldn't get confused on what to plug into. So I'm going to put -1 into F prime or S prime. Now, do I want to put it there or there? The bottom one's way easier. Do I even care if it comes out -100 or -1,000 or -2.7 or negative whatever? What do I care? If it's positive or negative. I just care if it's positive or negative. That's all I care about. So that makes this easy also. So I put a -1 into the 7th power. What is that? -1 to the 7th is what? Negative. I didn't care if it's -1. I don't care. It's negative, right? -1 to the 7th is negative times -72. Positive. -1 minus 1. It's -2. So that'd be a negative times, what did we say this was? Positive. What's negative times positive? So we're going to put a negative right there. Now we're going to put in 1/2. Now we thought, oh, this is going to be kind of a pain plugging in 1/2. But remember, we only care if it's positive or negative. So that's different than over here, right? We needed to know what the Y values were because we wanted to see what the highest was, what the lowest was. But here, we just care if it's positive or negative. Okay, put in a 1/2 to the 7th. That's going to be positive. Times negative. That's negative. 1/2 minus 1. Negative. So we got a negative times a negative. That's positive. Okay? What about 2? 2 to the 7th is positive. Times a negative. It's negative. 2 minus 1, positive. Negative times positive is negative. Aha, so what do we got? We got negative. See how that tells us the same information? It tells us the same information we're used to having. So now we can answer all the questions. A, where is F increasing? No.
Between 0 and 1.
0 and 1. Where is F increasing when F prime is positive? Now, we should say that right there. B. Now, the ones that really matters is local max min, and I'll get to that now. Where is F decreasing? Negative infinity, 0, 1, to infinity, and that's because F prime is negative. Now, I don't really care about those two so much, okay, to be honest with you. I don't really care about that. If it said justify your answer on those, it usually doesn't for increasing, decreasing, okay? But now, carefully, and this is in that video that I have up there as well, although some rules have changed on the AP test since I made that video, so I'm going to stress it even more. In C, where does the function have a local max? At x equals 1. Why? And it's going to say this on local max min every time. Justify your answer. Why? Here's what the AP, they made this change about 3 years ago to be very specific about this. They said number lines are okay, but they're not good enough for full justification. Just because you have a number line. Now, I'm going to give you a point for having a proper number line. But, and there are some other justifications you can use, possibly, like if you knew what this, if this was just a simple graph, if this was x squared plus 1 or something, or x squared minus 1, and you could just draw a graph and then go minus plus minus or something on the graph, that's the same information, so that'd be fine. So if you knew what the graph looked like without a calculator, right, you could do that. Or if it was a calculator problem and you wanted to graph you wanted to graph F prime and draw it on your paper and do that instead of the number line, I think that'd take longer actually, but whatever. But if you have the number line, that information, you'll get some points for that. But you have to have this in your answer. So you have to say F prime changes positive. Now, if I was doing this on an AP test or an actual test, I might write out the words. I might not try to shortcut it too much. But F prime changes positive to negative. So F changes what?
Increasing.
No, not concavity. Increasing to decreasing. Remember, F prime positive means F's increasing. F prime negative means F's decreasing. So you have to have both of those. AP made this very clear a few years back that they want to see the connection between F prime and F. Now, I did not make you do that so much on our last quiz on chapter 1. We were talking about this stuff. We were just getting started with it. This quiz, that is going to have to be there on local max min. Okay, and then D, where's the local min? X equals 0, and then same reason. F prime changes negative to positive, so F changes decreasing to increasing. You've got to make that change. You can't just say F changes decreasing, increasing. You can't just say F prime changes negative, positive. You've got to make that connection between F prime and F. So you've got to have those on there, but it comes from your number line. Okay? So do you see the connection, though, between what we were doing back in chapter 1? We had the F prime graph. We saw it did this. We knew where local max and mins were. We knew where the graph was increasing, decreasing. We knew all that stuff. Well, we're doing the same thing here with an equation where we don't know what the graph looks like. But what did we do? We did the derivative. We set it equal to 0. We found its stationary points, which is always the first thing we're looking for, is where does the F prime cross the x-axis? Now we want to know how it crosses. Does it just bump up? What if this would have went negative, negative, positive? What would you have had here? Flat spot. Negative, negative, positive would have been like my blue graph. It's negative, then it's 0, then it's negative, then it's positive. So you'd have had a flat spot there. Right? You'd have a flat spot. So when they said local min, you just said none, right? Or whatever. It's possible you don't have a local min, right? Or you might have several local mins. X equals 1 and 3 and 7. There might have been 3 local maxes, right? And then you don't need to write this out for all 3 of them. You can just put down all the local maxes and then your justification. Okay? So that's number 20. Now, what would have, let's talk about this real quick. What would have changed if this was, what would have changed if this would have said that S is a position function? A lot of times they use S for position. S of T, T would be time, from Bismarck. The position east of Bismarck, right? Let's talk through all the different things we found here. So S was the position function of miles east of Bismarck. What would S prime be then? The rate of change, the velocity. Not speed, but velocity. Miles per hour. So setting that equal to 0 would have got us what? What would that be? When the velocity 0 is when he stopped, right? So he was stopped at the beginning at 0. Remember, it was noon, right? So he stopped at noon and at 1. When we did this number line, what did that tell us? Now I labeled this S prime. I might dock you a point if you guys did that. S prime. Don't do that. I'm not getting graded, so I don't care. S prime. Okay. What does this number line tell you about the car? West, before noon, right? Before noon, west, east, west. So the question could have been, instead of where's the function increasing, where's the function decreasing, the question could have been, when is the car traveling west? When is the car traveling east? Right? Wouldn't you done the same thing? You'd have done the same thing. You'd have done all this same stuff. So here's the position of the car, S. When is it traveling west? When is it traveling east? Well, you'd say, well, it's traveling west when its velocity is negative. Its velocity is a derivative. How do we tell when the derivative is negative? So you got to understand this. How do you tell when a derivative is negative? Or how do you tell when the derivative is positive? What do you do? Before that. This is, okay, I tell you this is a derivative graph right here. When is this derivative positive? When it's above the x-axis. So tell me, when's it quit being positive? Okay, here's my point. My point is this. If I ask you, how do you tell if the derivative is positive or negative, the first thing you should answer me is, first find where the derivative is 0. Emily, see the difference? You said plug in numbers, but what numbers? Would you just start randomly, blindly plugging in numbers? Right? How do you tell when the derivative, so on this problem, oops. So on this problem, how do I tell when the derivative is negative or positive? I don't just start plugging in a 1 and a 2 and a 3 and a 4, right? Because I get a positive, then another positive, then another positive. I say, well, how do you know if it's ever going to quit being positive? You first have to find where the derivative is 0, right? So if I ever ask you that question again, how do you tell when the derivative is negative? Your answer to me is what? First find where the derivative is 0. First find where the derivative is 0, because the only way it can change from being negative to positive is what? Be 0. It's got to cross the x-axis. It can't change from positive to negative without first going through 0 unless it jumps, but then we have a break or something in the graph, and we're not going to have those right now. Okay? So the way you find if the derivative is negative or if the derivative is positive is you find where the derivative is 0, and then you check in between. And that's what we're doing. Okay, last problem, 52. We'll see how much of this we can do. This is, we're going to spend a lot of time working together here just so we understand. So this problem would be a little extreme as far as me expecting you to do this right now. So that's why we're going to talk about this one and kind of at least get it started in class. But on page 122, it says on 52, for which value of the constant k does the graph of y equals x cubed minus 3x squared plus k have just one x-intercept, 2 x-intercepts, 3 x-intercepts? Justify your answer. So there's a k in here. Now we're going to have problems all year long in the AP test where they have a K, it's some unknown constant problem, it always freaks us out. But you just work it like you normally would for the most part. So the function they give us is y equals x cubed minus 3x squared plus k. Now what's that k do to the graph? Just shifts it up and down. Now what's a normal cubic look like? Just a basic cubic. It could go up, down, it could be, the basic just x cubed is, but just an ordinary cubic. It could go up, down, up again, right? So, remember we had those questions about how many x-intercepts it could have, so couldn't it just have one? Couldn't it come up and do that? Right? It could just have one. It could come up and touch, so it could have two, right? Or it could come up, come back down, come back up, where it would have three, right? Now, so you see what I'm saying? If you keep shifting it up, so it could have one, shift it up a little ways, it could have two, shift it up a little farther, it could have three. Now, what happens if I keep shifting it up? Well, yeah, it could have two again when this touched. It could have two, and then keep shifting up, it could just have one, right? So the key, so that's the whole key to understanding this problem. The key to understanding this problem is noticing that when's it going to stop? So way down here, it's going to have one. When's it going to then all of a sudden have two? When that local max touches the x-axis. Now, you shift that up, and then it will have three, and then when will it quit having three and start and then have two again? When that local min touches the x-axis. And then if you keep shifting it up past that, it's back to one again, right? The key to the problem then seems to me figuring out where the local max and mins are, right? So that's the part of the problem that you would have, that if I just assigned you this problem, I think you would have struggled coming up with, right? You'd have struggled coming up with, how can I tell when it has one intercept or two intercepts or three intercepts? So what you notice is the K is the shift, and what's going to determine how many intercepts you have is where those max and mins are. So the first thing we got to do is find out what their x coordinates are. Where are the x local max and local mins? So that's how we're going to start this problem. So we're going to do y prime, which would be what? 3x squared minus 6x. And what's the derivative of a constant k? That's the key. It disappears, right? We can find, because remember, the k just shifts this up and down. So we can find where the local max and mins are, the x values. We don't care about the y values. Well, we're going to here in a minute, just because we want to see when it's touching the x-axis, but that's what makes this problem a little different. So we factor out a 3x. That leaves me x minus 2 equals 0. So my x max and mins have to be at 0 and 2. Right? Now, here would be a great example. Let me just throw this out there. This would be a great example of a problem where you wouldn't really have to do a number line to tell that you have a local max and min. Most of the time we do, because we don't have such simple graphs. But on this one, you have two reasons you could. You could say, well, this is a cubic. The leading coefficient is positive, so don't you know this goes up first? Right? We learned that about cubics. So you could write that out. You could say, this is a cubic with a leading coefficient is positive. I know the graph looks like this. So the first one is a local max. The second one's a local min. It couldn't even be a flat spot. There's no way to be a flat spot, because if it's a flat spot, then it's got to keep going up. Then it's got to do that. Well, then that doesn't look like a cubic anymore, right? So it's got, so we know. So we could do a number line and all that stuff, but we wouldn't have to, because we could do that. But we could go through the same process, do a number line. So we know we're going to have a local max at x equals 0. And we know you're going to look at this a day from now, and you're going to go back and go, how did we know that was a local max and local min? Okay, but we know that's where they're going to be. All right, so now the question is to go in and plug in those values. Because what we want to do is we want to see what, okay, we want to see Because remember, what we care about here, now this, again, this is not a normal type problem. You'll never do, yeah, I mean, well, I want to say never. It could show up somewhere, something similar to this, where you have to kind of think through this kind of thing. But of all the stuff we've done today, by far the most important problem is 24, global max min, 20, local max min. Be able to mimic, be able to go through the way we've done these problems. These are the key, right? But it doesn't hurt to kind of stretch us and make us think a little bit about this process and what's going on to now apply this in a different kind of problem, okay? So now what I'm going to do is I'm going to plug these back in the original. Now normally we don't. Local max min problem is more like this. We just care where's the local max min, number line, all that stuff. But what we're trying to decide is where has this been shifted? So we want to know on this local max at 0, we want to know what that is. So you plug in a 0, what do you get? You just get K. And what about when you plug in a 2? You get 8 minus 12 plus K. You get negative 4 plus K. Right? Okay. So now, when is there going to be one intercept? You're going to have to finish his life. We're going to have one intercept when the max is what? Below 0. And the max, of course, is this one, right? So it's going to be when K is less than 0, right? When this Y value right here is less than 0, we got this situation. But also, you're going to have one when the min is where? No. You're going to have one when this shifts up to where this minimum is greater than 0. Now, what's the minimum? So it's going to be when negative 4 plus K is greater than 0, which would be when K is greater than 4, right? So I'm going to leave you to find the rest of it. So what has to happen for there to be 2 intercepts? What has to happen for there to be 3 intercepts? Okay, we just figured out what K has to be for there to be 1 intercept based on that. Okay, so that's what we just went through there. All right, your homework is going to be in section 2.4, and it's going to be 3 through 12, 19, 23, 25, 35, 44, 46, and 54. Now you figure we did about 2 problems in an hour and a half, and you've got all those, so better plan on 6-7 hours old. Probably not. But 19, 23, and 25 are really the key ones. Those are the ones you really have to, you're going to be spending your time on. Remember, 19 is going to be like 20. 19 is going to be your local max min one. 23 and 25 are going to be like 24. Okay? Very important that you spend a lot of time on this, that you work hard on this, because this is a big part of our next quiz. Local max min, number line, list of candidates like we did the global max min problem. It's a very fundamental idea that we're going to see over and over again.